G'day, it's Richard Marr from Marr's Classes again. Today we're going to have a look at a way to derive a mathematical expression. Quite often in your study of high school physics, your teacher will say, oh look, the maths is beyond you, just accept this equation. We're not going to do that today. We're going to look at how we can derive the expression for centripetal acceleration. Now, centripetal force or centripetal acceleration occurs when an object moves in a circle. So just imagine that rock is on a string and being spun around in a circle. The string will always be applying a force toward the centre of the circle. So you've got a force acting along the string, and it's always at right angles to the velocity. So let's just imagine that this object is travelling part the way around the circle, and at all times you'll notice that the force is always being applied perpendicularly to the velocity. Okay, now when it travels, it is travelling around a curve. So let's just have a look at these 2 points along the curve where you've got an initial velocity vi and a final velocity vf. If we were to add those two velocities, all we'll end up with is the sum of the velocities, and it really won't tell you too much. But if, however, we got the opposite of the initial velocity and we added that to the final velocity, final velocity plus the opposite of the initial velocity, it's the same as saying the final velocity take the initial velocity. And when you look at final take initial, it's equivalent to the change in velocity. So by adding the inverse of the initial velocity to the final velocity, we are finding out how the velocity has changed. Now that will be important because we know that acceleration is the rate of change of velocity, in other words delta v on t. So let's now have a look at the equation that we have here of the delta v. If we have a look at that, and we also consider the diagram we've got at the bottom compared to the diagram we've got at the top of the screen. The diagram at the top of the screen is the physical situation where we've got r as representing the length of the radius of the circle, or the length of the string, and s is the distance that the object has travelled around the circumference of the circle. Now, if we were to get the radii closer and closer, the angle between them getting closer and closer to zero, we'd see that the length of the arc that it travels will approximate eventually a straight line. So let's just make a big assumption and say that S is equivalent to a straight line. And if that's the case, we've now got two triangles that are similar, and they're similar in that they are both isosceles right triangles. Now, whenever you look at an isosceles right triangle, you'll notice that the ratio of the hypotenuse to the length of the hypotenuse to the length of one of the sides will be the same in any isosceles right triangle. In this case, we've got delta v on v will be equivalent ratio to s on r. Now, what do we know about s? We know that s is the distance travelled, and the distance travelled is equivalent to the speed multiplied by the time. So we could then say that s is v on t. So instead of saying s on r, we can say vt on r. So now we've got another expression of the two ratios. So let's have a look at that final ratio that we've got there, delta v on v equals vt on r. And let's just do some manipulation of it. First of all, let's just do some cross multiplication and bring the v from the denominator on the left-hand side to the numerator on the right-hand side, and t from the numerator on the right-hand side to the denominator on the left-hand side. So when we do that, we'll now get this expression here. Now, on the very left-hand side, we've got delta v on t. We've already said previously that delta v is equivalent to the final velocity take the initial velocity. So let's substitute that in. And on the right-hand side, well, we've got v times v. That's the same as v squared. Now, when we've got the final take the initial velocity divided by the time, that's the expression that we use to determine the acceleration. So we now know that the acceleration equals final velocity take initial velocity on time, and it's also equivalent to v squared on r. So what we've actually calculated now, or not calculated, but derived now, is an expression for the centripetal acceleration. You didn't need to use any calculus, you didn't need to use any fancy or high-level mathematics. It was all done with straight algebra. So that expression for the centripetal acceleration can be then substituted into Newton's second law, which is F equals ma, and we can get the expression for the centripetal force, and that is mv squared on r.